Hello everyone. Let's talk about the optimum filters. Estimation of a signal from another signal is one of the most important issues in signal processing because it embraces a wide range of very good applications. In many of these applications, the desired signal, sometimes it is a speech signal, sometimes it is a radar signal, or sometimes it is an EEG, medical signals, or even an image is not available in pure form, or it is not observed directly. For variety of reasons, the desired signal will always be contaminated with noise and distorted. So the equipment used to measure the signal may be of important equipment, sensor, which is of limited resolution. The signal may be observed in the presence of noise or other interfering distortions. It is distorted due to the propagation of signal from the source to the receiver. Source to receiver. You will find out that mostly starting from the pickup point where the sensors pick up the signals till the various amplification units and the display units and communication units, digital communication systems through which it travels, obviously it is getting distorted. In very simple idealized environment, it may be possible to design a classic filter. What are called as classic filters? Classic filters like low pass filter or sometimes high pass filter, or even for example the band pass filter or band stop filter for this matter, those filters which we have studied in DSP, sometimes it is possible to restore the desired signal from the measured data. Only in idealized environments. Rarely, I don't think that these filters will be optimum in the sense of producing the best estimate of the signal. So what is the objective? We are in the process of producing the best estimate of the desired signal in a noisy, from a noisy observation, distorted observation. The best filters will be digital filters, Wiener filter. The other one will be, they call us, there is a reason behind it, discrete Kalman filter. So this is digital Wiener filter. The other one is discrete Kalman filters. In 1940s, because of the interesting usages during World War, applications in communication theory, especially Wiener, pioneered the research work in the problem of designing a filter that would produce the optimum estimate of a signal from a noisy measurement. Optimum estimate. Optimum estimate. Designing a filter. Optimum estimate. Optimum estimate from a noisy measurement. This filter he identified as Wiener filter. The discrete form of the Wiener filter may be used to design or recover a signal from noisy observation. See, X of n is equal to D of n plus V of n. Objective is to extract only D of n or D cap of n, assuming that both D of n and V of n are Whiteson stationary random process. Okay. Random process. Wiener considered the problem of designing a filter that would produce the minimum mean squared estimate. I would put it in this way. By applying x of n as an input to the filter, which is a noisy observation, where this is called white noise, V of n, where D of n is the desired signal, right? D of n, V of n are said to be Whiteson stationary random processes. You should estimate what is the output. This is the filter. The filter, let me call this is Wiener filter. It produces an estimate d cap of n. You should design a filter such that it will estimate the desired signal such that the error will be very minimum, not this direct error. Minimum mean, it should produce minimum mean squared estimate. The problem of designing the filter that would produce. Problem of designing a filter that would produce minimum mean squared error or minimum mean squared estimate of D of n is the objective of aim of Wiener filter. What is E of n? It is the difference between D of n and D cap of n. Okay. We will illustrate it using a diagram. We have a filter which is called as Wiener filter, which will have W of n as its impulse response. Normally in Z domain it is represented as W of Z, to which an input is applied. The input is, say for example, the input is right, the noisy observation, where it is expected to produce the estimate, minimum mean squared estimate, the desired signal. Okay, minimum statistically, where x of n is equal to D of n plus V of n, but D of n and V of n are said to be statistically related to each other, and they are Whiteson stationary processes. The filter W of Z is to produce minimum mean square estimate, which is called D cap of n. In order to ensure that it has produced minimum mean squared estimate, you can just have the line called D of n, where you can just apply. D of n is the reference, D cap of n is the output produced by you. It is expected to produce E of n. Illustration of Wiener filtering problem with the two Whiteson stationary random processes x of n and D of n. They are statistically related to each other. The filter is represented by W of Z, which will produce minimum mean squared error estimate, D cap of n, of D of n. So, design a filter that minimizes epsilon or zeta. I can put it like this. So, what is W of Z? Now, at the beginning stage, people introduce W of Z as linear shift invariant filter. Okay? The filter is applied with an input signal x of n, and it is expected to produce minimum mean square estimate D cap of n of another signal D of n. So, what is the input? What is the output? What is the expectation? All are necessarily to be mentioned out. Before proceeding further, we should assume that D of n and V of n are related with each other and they are WSS, random process. We shall start discussing about the types of Wiener filters and their problems in which they are used. For example, the classical problem which we have considered just before few seconds, where x of n is equal to d of n plus v of n is the input to w of z, which is supposed to produce d cap of n of d of n, minimum mean squared estimate, using a causal filter. Let me call this as a causal filter, linear time invariant filter, causal filter, estimate d cap of n of d of n from the current and past samples of x of n, because it's a causal filter. So you require current sample input as well as the past input samples. This is the first category, classical filtering problem. The second one is so interesting, similar to filtering problem, except that the filter is allowed to be non-causal. W of z is allowed to be non-causal. How is it possible? Is it realizable? Can you estimate d cap of n of d of n from not only from its present and past input samples? Will it be possible to estimate it from its future samples also? Let's see. Is it non-causal or not? So here the x of n is equal to d of n plus v of n, no doubt. This w of z is, yes, this is the filter which is supposed to produce d cap of n, which is supposed to produce the minimum mean squared error. Minimum mean squared error, estimate of d cap of n. But one and only difference is the filter is allowed to be non-causal. Right? Estimate d cap of n from x of n using all the available data. Third important category. So interesting. If the desired signal is the next sample, I will repeat, the desired signal is the next sample, it does the operation called prediction, where W of z is a causal filter, there is no doubt. Rarely we used to declare that as a non-causal filter, so that it can estimate d cap of n from all the available data. So when I apply x of n is its input, which is the noisy observation, desired plus noise, which produces d cap of n, right? But d cap of n with the minimum mean squared error estimate, isn't it? Right. All right. But this time d cap of n is an estimate of the next sample. So the Wiener filter becomes a linear predictor. The filter is about to produce prediction of next sample in terms of linear combination of previous samples. That's why we say it is a causal predictor. Present sample and its previous samples will all be used to estimate the next sample, predict the next sample, linear combination of previous values. Whereas the last category in which the Wiener problem filtering framework could be used, right? It is called deconvolution issue. How deconvolution is performed? Say for example, when the signal is totally contaminated and embedded inside a new sample sequence. Say for example, d of n is convolved with g of n and then it is corrupted by noise, distorted by noise. What is g of n? Let me call this as unit sample or impulse response. Response of a linear shift invariant filter. That time, if you could estimate with this x of n, if you apply through a Wiener filter, the Wiener filter, if it produces d cap of n, despite the results of convolution and corruption, corrupted by white noise, that time what you are obtaining or designing is called deconvolution framework. Deconvolution Wiener filter. Did you understand this? Right. So, design of FIR Wiener filters are derivation of discrete form of Wiener Hop equations. Wiener Hop equations are the mandatory equations which specify the filter coefficients of optimum filters. What is meant by optimum? Optimum in the sense the filter which could produce minimum mean squared error. So solutions to the Wiener Hop equations in the case of regular classical filtering, or in the case of smoothing operation, or in the case of prediction operation, or in the case of deconvolution operation, right? So solutions to Wiener Hop equations is the mandatory part to design Wiener filters. They can be called as FIR Wiener filters. Of course, there is a secondary part which is called design of IER Wiener filters. Wiener filter, FIR Wiener filter, IER Wiener filter, causal Wiener filter, non-causal Wiener filter. So obviously designing a causal Wiener filter is little bit easy, whereas when you design non-causal Wiener filter, you need to take certain factors into consideration. So unlike the non-causal Wiener filter, solving the optimum causal Wiener filter is a non-linear problem that requires spectral factorization of power spectrum of the input processes. Spectral factorization of power spectrum of the input processes will be useful for design of optimum causal Wiener filters. So Wiener filtering, Wiener smoothing, Wiener prediction, Wiener deconvolution, how many different varieties are there? Let's see. Right? One after the other in the next video. So let me give you the statements. What are all the next topics to be covered? We will concentrate on FIR Wiener filter, the next one is called in the name of derivation of Wiener Hop equations, which gives you the relationship between filter coefficients of optimum. What is meant by optimum? A filter which produces minimum mean square estimate. Optimum filter, and then we will think about solutions of Wiener Hop equations. Unless otherwise you solve them, you cannot design a classical Wiener filter for filtering, or you cannot go for smoothing, or for this matter even you can take a predictor design, or you can think about using Wiener filters as a deconvolver, deconvolution. For all these cases you need to solve Wiener Hop equations. Of course, when you think about FIR Wiener filters, the derivation of Wiener Hop equations and then solution of Wiener Hop equations, obviously you need to think about IER filters also, IER Wiener filters. In the case of IER Wiener filters, we'll see the recursive pattern of it, and then we will solve non-causal Wiener filtering issues also. The problem of designing causal Wiener filter, non-causal Wiener filter. In the case of non-causal Wiener filter, solving the optimal causal linear filter equation, as a non-linear problem that requires a spectral factorization of the power spectrum of input processes. All those things will be discussed in the next video.